Hi, hello friends. Welcome to T Academy. In this video, we'll continue the Tsgenco AW Solutions 2024, and the question here is from the networks, and a very simple question here. In this question, the examiner asked to find the power delivered by the voltage source as a function of A. Okay, that's we need to find. Generally, we will write the formula for power. So power delivered or power is nothing but it's a product of voltage into current, we know. Okay, in this question also voltage source is there, current is there, so which is nothing but P is equal to V into I, but as a function of A we need to calculate here. So P is equal to V into I. As a function of A you need to write means here you have to apply the KCL. So once you apply KCL, then you are going to find the value of power in terms of A here. What is a I1? Current entering at the terminal, I will take it as a minus I here, and current leaving from this terminal, I will take it as a plus sign, and current entering at the terminal, I will consider as a minus sign here. So here this one is a current controlled current source here. So from this point, so what is the value of I here? So I is nothing but I1 minus A into I1. Okay, that's nothing but I1 into 1 minus A will be the point here. Now, what is a P? So P is nothing but V into I. So instead of I can write I1 into 1 minus A. What is a V? V is nothing but, so this voltage source and this resistor and this current controlled current source are in parallel. So I can write that the voltage across a voltage source is the same as that of the voltage across a resistor. So that I can write, so V is nothing but I1 into R into I1 into 1 minus A. Okay, which is equal to I1 square into R into 1 minus A will be the answer. But here in the given options, they written the equations in terms of voltages. So what I can write is, so I1 is nothing but in this network, which is nothing but V by R I can write. So that V square by R square into R into 1 minus A. If you simplify this one, so V square by R into 1 minus A is the right answer for this question here. So the answer will be 2 here. Let's move to the next question in the same subject of networks. This is also Tsgenco AW solution paper here, question here. So in this question, find the current ID. So current ID here flowing through the diode and the VAB voltage in the circuit shown in the figure. Assume the diode is ideal here. Okay. So can we apply superposition theorem here? So superposition theorem is valid only for the linear networks. Okay, so diode is a non-linear element. Okay, so what we will do is, so we need to simplify this network. So what I am going to do is, I am going to use with the help of source transformation technique. Okay, so based on this, I will convert voltage source in series with resistance can be represented as current source in a parallel with resistance here. Already you know about that. So I am going to convert this voltage source in series with resistance here, and similarly current source in parallel with resistance I will also convert into voltage source in series with the resistance here. So like that I will modify and I will do the network here. Okay, so first of all what we will do is 10 is in series to 4, so I is nothing but 10 by 4, which is equal to 2.5 amps. Okay, so first of all I will take it as, so 2.5 amps of current, and resistance is in series here, now it becomes in parallel 4. Okay, So I am not disturbing this terminals A and B here, and I am keeping the diode as ideal one like this, and current source is in parallel with resistance. I will convert. So V is equal to 2 into 1 I into R, so that is 2 volts, and here is in parallel, it will become in series here now. So 2 volts here. Okay, so I forgot to mention here, here there is a 1 4 ohm resistor here between the terminals A and B. Now what will is, I will combine these two. So I will combine these two here and I will make it like this. So after making the combination here, so current source of 2.5 amperes will flow, and this parallel combination will give equivalent resistance of how much? It's a 2 ohms, and here we have a terminal A and a diode like this, and there is a resistor, okay, is in series with the voltage source here. So 2 volts and 1 ohm here. Now I will remodify this network again. So what I am going to do is, I will make this circuit into its equivalent voltage form. So when we are multiplying, so 2.5 into 2 it is nothing but plus or minus 2.5 into 2 is nothing but 5 volts here. So 5 volt source. Now the resistance is in series here, 2 ohms as it is, and the point A here, and the diode and the resistor, and here we have voltage source of 2 volts here, okay, 1 ohm here. Now so next what we are going to do is, I am going to apply the loop analysis to find the current here, okay. So minus 5 volts plus, let me assume this current is I1, so 2 into I1, and the diode is ideal, okay. So if you see here, it's a higher potential here compared to here, so the diode will conduct and the current will flow, okay. Why? Because if you take the anode to cathode, so VAK should be greater than 0, okay, and the diode is ideal, so that the diode is, assuming that I am conducting the diode here, okay. So minus 5 plus 2I1 plus I1 plus 2 is equal to 0, okay. So I am writing the equation here. So by simplifying this equation, so we will get I1 as 1 ampere, okay. So I1 as 1 ampere, that means the diode is conducting here. Now next question, in this question they asked what is VAB. So VAB you need to calculate, so for which I'll take the same equation here. So I am assuming that the VAB is here, so plus minus here, okay. So minus 5 volts plus 2 into I1 value, you know, series current means it's a 1 plus VAB is equal to 0. So VAB is equal to how much? It is nothing but 3 volts here. That means in the given network, the current flowing through the diode is 1 ampere, and the voltage across these terminals will be equal to 3 volts here. So the final answer will be 1 amp 3 volts here. Thank you friends, have a nice day. If you like this video, please subscribe to my channel and share with your friends. Thank you.